In this problem, we're trying to show whether these two are equivalent or not. And so what we're going to do is use a single truth table to construct the truth table column for each of these compound statements. And if they have exactly the same true and false values in exactly the same order, then these two compound statements are logically equivalent. If not, they're not. So heading for this one, let's do P implies Q first. And the only way that can be a broken promise is if the P is true and the Q is false. So this is a broken promise. The rest are true. And then let's negate that. And to negate this statement of P implies Q, we just switch all the truth values. And so that's kind of the first part of the problem. Now we're going to head for this. In order to get there, we need a not Q, the negation of Q, which is false, true, false, true. And then we need a P and a not Q. The not Q is here, the P is here, and when we do an AND on those two things, the only way that it can be true is if they're both true, and that looks like it's this one, because we have a true here and a true here. The rest of them have at least one false. In fact, the rest of them then are false. Now we look at this compound statement and this compound statement, and we compare them row by row, false, false, true, true, false, 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 false. So they're equivalent in terms of their truthfulness based on the truth values of P and Q. And so we call these equivalent. If even one of these didn't match, they would not be equivalent, but these are equivalent. Like the last problem, we're going to see if these two compound statements are equivalent. Notice they both have P and Q or R. It's just a question of which two we're doing first. So if they are equivalent, it would be kind of like an associative property, but not exactly. So let's go with the Q or R first. And we're looking at these two, and OR is always true unless there's two falses. So here's two falses, here's two more. So everything else is going to be true. And then we need a P and this Q or R. So we're doing Q or R and P. And so AND is only true when both are true. So it's true here, it's true here, it's true here, and it's false everywhere else. So this is one of the two columns that we're going to compare for being equivalent. It's this compound statement. The next one we do a P and Q. And the P and Q is the first two, and it's true when both are true. And that's it. It's false the rest of the time. And then we're going to do the P and Q or R by comparing this one and this one. And we're comparing them with an OR, so that's almost always true unless we get a couple of falses. We get a couple of falses here and here and here. Now I'm not at all sure about that. Somehow my brain is not seeing them well, so I'm going to double check. R and P and Q both true. R, one of them's true, R, one of them's true, R, one of them's true, R, one of them's true. So I think we have true, 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 false, true, false, true, false. little vague on that for some reason, but notice it doesn't really matter, because for these to be equivalent, they have to be an exact match. And these two compound statements are not at all an exact match. This has a big long string of falses. This has some trues thrown in. So these are not equivalent logically. We could try to solve this problem without using De Morgan's laws, but we're asked to use them. So according to one of the two laws, this quantity, you can sort of distribute the negation sign through and then change the or to and or vice versa. So De Morgan's laws says that this is equivalent to this. But now we're comparing it to this statement. In the negation of P and the negation of Q, and is different than or. And is usually false and or is usually true. So these two are not going to be equivalent, and I feel like I can state that without proving it with a truth table, because ors and ands are very, very different than each other when you have a healthy spread of true-false values. So, not equivalent. Again, according to De Morgan's laws, we can distribute this negation through kind of the parentheses. So we will have the negation of P. The and turns to or, and then we'll have the negation of Q. The negation of P is P itself. And we have or not Q. And so by De Morgan's laws, this is equivalent to this, but these guys are equal. So this one is equivalent to this. And of course, if you wanted to double check this, you could do a truth table on this and a truth table on this and see that they had exactly the same true and false values. But we're supposed to take the shortcut of De Morgan's laws. Once again, De Morgan's laws applies to the negation of an and or an or statement, and it basically says that you can distribute through the negation as long as you turn the and to or the or to and. And so by De Morgan's laws, this negation can be distributed to the P, the and becomes or, and it gets distributed to the negation of R. So it's the negation of R. It's two negations in a row. So that can be simplified into just R, in which case we have a match. Exactly. So we've shown that this is equivalent to this. Without the use of a heavy-duty truth table, we've saved time. So they are equivalent by using De Morgan's laws.